Hello, and welcome to Lecture 6 of Electric Fields in Phys 1204. In this lecture, we're going to look at the field due to an infinite plane of charge, and that may sound like an awfully abstract and kind of useless topic, because I'm sure you have never come across an infinite plane of charge in your day-to-day life, but it turns out to be one of the most useful electric fields we can calculate. In the previous lecture, you saw the field due to a thin, uniformly charged ring for a point along the symmetry axis of the ring. And if, by the time you see this, I have got a supplementary lecture built, then you will have seen the field due to a uniformly charged disk. And the reason I've colored it this way in the picture is that we find this field by thinking of the disk as a set of nested rings. And so we're able to use the ring expression to get the disk expression. And note that this lambda here is the linear charge density on the ring, whereas this sigma here is the surface charge density on the disk. And what I'm showing are the magnitudes of the E-fields. In both cases, they point as shown in the diagram, assuming the charge on these objects is positive. Now, neither of these field expressions is actually particularly useful, because you don't really often have to deal with charged rings, and charged disks are somewhat common, but not all that common. However, we're going to use this charged disk expression to get an expression for something far more useful. The way we're going to do this is we're going to take one more limit. So here's our expression for the magnitude of the field due to a disk of radius r. And we're going to take the limit of a very large disk. Or similarly, you could think, instead of the size of the disk getting very large, you could think of the point P being very close to the disk. What we're really doing is saying that the size of the disk compared to the distance that we're looking from the disk is very large. And so we're thinking of letting the radius of the disk going to infinity, or equivalently, we're thinking of z going to 0. These limits are the same. And so if you think about this part in the denominator, z squared plus r squared is going to go to r squared. You can neglect the z squared if either r is very large or z is very small. And so that means that this whole fraction here goes to just z over the square root of r squared, or z over r, and either way, if z is going to 0 or r is getting very large, that goes to 0. So this whole fraction disappears from the expression, and we're left with a very simple electric field strength expression. And what we've just got, since we've taken our disk and let it get infinitely large, is the electric field due to an infinite plane. So what we've just seen is that for an infinite, uniformly charged plane, we get an E field given by this expression. And if the plane is positively charged, that E field points away from the plane everywhere, whether you're looking above it or below it. And it's perpendicular to the plane everywhere. Note that there is no z or any other coordinate in this E-field expression. So this is a uniform electric field. This is the way we get a uniform field, with an infinite plane of charge. And note that we can represent it, instead of with a field vector diagram, with a field line diagram this way, in which case we have electric field lines that are parallel and evenly spaced. Well, you may not be very impressed with this result, because when have you ever come across an infinite plane of charge? Certainly never, and so it seems sort of useless. Except that this is a good approximation for the field if you're looking very close to any charged surface. Realize that just as when you walk outside and look, you don't notice the curvature of the Earth, when you look very close to any surface, if you look from close enough, the surface looks flat and infinite. And so the field close to any charged surface, where by close we mean on a scale that is smaller, much smaller than the curvature of the surface, the field always looks like the field due to an infinite plane of charge. We can find another use for this expression if we think about what will at first seem like a contrived situation, but actually turns out to come up all the time. Let's think of two planes. They're not infinite. They have some area A, same area of each, and they're separated by some distance d. And they have opposite charges, opposite signs, but the same magnitude of charge. And let's think about a case where the smallest dimension of either of these plates is some distance L, and we're letting d be much less than L. So that's not what's shown in this picture. Here, d and L look of similar size, but we're really thinking about the case where these plates are very, very close together compared to their smallest dimension. If we're doing that, then anywhere in between the planes, we must be very, very close to the planes. And so we can treat them as infinite, because the edges of the planes are very far away compared to the distance to them. So now let's think about any place in between the planes far from the edges, so that the distance to the plane, either plane, is very small compared to the distance out to the edges. And since we can treat them as infinite, that means each plane will be producing a roughly uniform field here. And so the positive plane will be producing an E field pointing away from it. The negative plane will be producing a field towards it. Well, notice that these two fields are in the same direction. And they have the same magnitude. They each just have this magnitude, the expression we got for an infinite plane. And since they're in exactly the same direction, we can just add those magnitudes together to get the magnitude of the total field, like so. So as long as you look far from the edges, or we would say deep between the planes, the field is uniform everywhere. If you look near the edges, unlike in this picture, in fact what happens is that the E field lines bend outward and the field is a little weaker out near the edges of the plates. And the E field has a uniform magnitude like so, everywhere deep between the plates. And the field points from the positive plate to the negative plate. Note that, unlike in pictures like this, which you'll often see in textbooks, don't be fooled. This is a three-dimensional situation. A little hard to draw, but here's an attempt at it. That's the field between the planes. What about outside? Well, outside the edges, things are complicated, but a place that isn't complicated is if you look near to the planes and outside them, like what I've marked here. At a place like this, the positive plane, once again, is producing an E field that is away from it. And the negative plane is still producing an E field that points towards it. And again, these have equal magnitude, that magnitude that we get due to an infinite plane, and they're in exactly opposite directions, and so they cancel. And the E field here is 0. And so when we draw a picture like this, we really do mean that there's a uniform field in between the planes, and also, as drawn, there's a 0 field outside the planes. There are many, many applications where we end up having two plates that are parallel and oppositely charged, and if they're fairly close together, we can use the approximations that we just got. One of the most common applications is something called a parallel plate capacitor, and we're going to come across this over and over again in the course. The purpose of this device won't be particularly clear to you at the moment. It'll become clearer as we go on in the course. They look typically like this. If you open up some piece of electronics, you'll find a fair number of things that look roughly like this. And this actually contains two parallel plates, although looking at the shape of it, it's sort of hard to figure out how they'd be oriented. That's because the two plates are held apart by a specially chosen material called a dielectric, and then rolled up around each other. The fact that they're then curved doesn't matter, because the distance between the plates is very small compared to the radius of curvature, and so they can still be treated as flat parallel plates for purposes of calculating the electric field in between them. Well, we've just come up with what is probably a rather bewildering array of E-field expressions for different sorts of objects. So let me help you out and go through them and point out what is and is not important. So we started with the E-field due to a charged particle. And incidentally, the force due to a charged particle, which we find due to Coulomb's law, also applies to a uniformly charged sphere, although I haven't showed that. In any case, that means that this E-field expression applies to both charged particles and to uniformly charged spheres. This is foundational. This is extremely important. It was our starting point, and we derived everything else from it. But then we got a variety of other expressions for various objects. We got the E-field for a line of charge, and the E-field due to a thin ring, and the E-field due to a disk. Now, while the charged particle expression is important and foundational, these other ones are not important. They're so unimportant, I wouldn't even put them on a cheat sheet preparing for an exam. If I ever want you to use them, I'll provide them for you. However, what is important was the method we used to get them, and I do expect you to be able to carry out that sort of method, at least for fairly simple situations like a rod. So setting aside those unimportant ones, we then went on and used the expression for the E-field due to a disk to get the E-field due to an infinite plane. And from there, it was one quick, simple step to get the E-field due to a parallel plate capacitor, or two infinite planes of opposite charge. These expressions are important. Luckily, they're also very simple. But we're going to use these ones over and over again, just as we'll also use the expression for the E-field due to a charged particle. So don't get all bent out of shape about these unimportant expressions for things like thin rods and rings. What is important about them is not the expressions, it was the method we used to get them. These expressions are the ones that are actually useful.